Hello, and thank you for tuning in to this presentation of MINT, Discretely Integrable Moments for Symmetric Frame Fields. My name is Josh Vector, and this work was done in collaboration with Zhen Chen and Etienne Vuga at UT Austin. It was presented at the Symposium for Geometry Processing in 2025 in Bilbao, Spain, in the Basque Country. This talk will be organized into three parts. In the first part, I'll introduce some background concepts useful for understanding the task of volumetric parametrization. Then, I'll move on to the key contributions of our method. First, I'll discuss the novel mixed moment representation of symmetric frames which we study. Then, I'll discuss the first known exact discretization of symmetric integrability which we develop leveraging our mixed moment representation of frames. I'll also discuss several additional symmetric fairness objectives which we combine in order to develop a proof of concept boundary-aligned frame field design objective. In the results section, I'll discuss the evaluation of this design objective on two large datasets of volumetric models and establish that our formulation of symmetric integrability shows practical promise in addition to theoretical soundness. To begin, I want to discuss the problem of extracting coherent structures from fields. For instance, for applications in architecture, such as in the Guggenheim Museum, in the surface of the Guggenheim Museum in Bilbao. To begin, I want to start by thinking about just vector fields, such as a magnetic field. So if you take a magnet and you bring it close to a sheet of paper, and you sprinkle iron filings on the sheet of paper, the iron filings exhibit characteristic streamlines of a characteristic pattern, which follows the streamlines of the underlying vector field. In geometry processing, we're often interested in studying more complex fields, such as fields which track multiple vectors at every point. And for such fields, one can still trace streamlines of the field. But for some geometry processing applications, for instance, if you want to make a lightweight truss structure, it's interesting to try to extract coherent structures which follow these streamlines, but evenly sample the underlying geometric domain. So these figures are taken from Stutz et al. In 2022, and I want to point out the kind of visual resemblance between this multilaminar structure that they studied here and the Cetas de Sevilla, or the Metropole parasol, which was marketed as the world's largest structure when it was built. This is just to point out that it's interesting for certain applications to extract coherent structures, but the type of structures that one wants to extract is a bit application dependent. And that's because the symmetry of the underlying fields, which best model the problem, are similarly application dependent. For instance, in models of liquid crystals, the natural field to study is a line field, not a vector field. In models of the reconstruction of neural tracts from diffusion tensor image data, individual fibers in the brain might cross each other, and the labels of these fibers might be ambiguous. And then in this example, in this topology optimization example from Aurora et al. In 2019, they attempt to fit a lattice structure to a stress tensor field extracted from the finite element method. And here, both the signs and the labels of the underlying field are ambiguous. And this is the notion of symmetry that we'll be focusing on for the rest of the presentation. In particular, this notion of symmetry is often called octahedral symmetry. And it's the same sort of symmetry which is exhibited by this children's toy called a JAX. So now let's consider the problem of parametrizing the position of one of these JAX in space. And I want to begin by thinking about how do you parameterize the position of one of these toys by a set of three vectors. Now, the first thing to notice is that this JAX has the representational symmetry of the octahedral group. And what this means is that we can switch the signs or the labels of any of these vectors, and the underlying position of the toy in space won't change. And one thing that I want to point out here is that this is exactly the same representational symmetry of an unmarked cube. If you want to parameterize the position of a cube in space with three vectors, you can switch the labels or the signs of the vectors, and the cube will still remain the same. In this paper, we're interested in studying a larger space called GL3, quotiented by the octahedral group. And this includes frames which are both non-unit and non-orthogonal. Uh, but fundamentally, this doesn't create much of a difference, and there's still 48 different ways of parameterizing an element of GL3 mod O with frames. Okay, but this is a good start. So now we have some way of kind of describing elements of GL3 mod O. In geometry processing, we're often interested in solving geometric optimization problems. So now we want to think about how can we attach one of these elements of GL3 mod O to every point in space. So in order to do this, the first natural question is, well, how should we measure smoothness? And discretely, this involves coming up with a notion of how do you compare two discrete elements of GL3 mod O. A natural first approach is to consider this representation of GL3 mod O using frames, but now our notion of smoothness requires considering all 48 different permutations for every pair of adjacent frames. And so this makes it quite difficult to use this representation in practice. For instance, consider this smooth GL3 mod O frame field on a hyperboloid. Here you can see that the underlying frame field is clearly varying smoothly, but it's equivalent to this frame field. And so this makes the energy landscape of this problem extremely non-convex. And so the thing that we would really want to be able to do is uniquely describe every single element of GL3 mod O instead of needing to look over all of these 48 synonyms at every time we want to make a comparison. Okay, so how do we do this? Well, to approach the problem, we leverage previous work in geometry processing that studied representations of SO3 mod O over the fourth band of spherical harmonic coefficients. And this is a long line of work which was started by Huang et al. In 2011, and there's still research that continues on this representation today. But the basic idea is that you can take some canonical octahedral frame and consider rotations of it, and then you can represent it using in the fourth band of spherical harmonics, and then we can and then it turns out that there's a way to rotate these elements of spherical harmonics, and then our notion of smoothness is just going to be an inner product between these vectors in R9 of these coefficients of spherical harmonics. And so this representation was developed to study the problem of boundary aligned parameterization. So I want to introduce this problem a little bit at this point. So what is the problem of boundary aligned parameterization? Well, suppose you have some geometric domain like this triangular prism. We want to compute a map F from the geometric domain into a parametric domain, which is like Minecraft. And so the idea is that we want to send the boundary of the geometric domain to integer grid planes in the parametric domain. And if you can compute such a map F, then you can compute its inverse and send the Minecraft blocks back into the geometric domain. And this lets you kind of evenly discretize the original geometric domain into these approximately cube-like shapes called hexahedron. And the key challenge of this problem, of this task, is to compute this original map F. And so a promising approach to computing this parametric map F is to break it up into two parts and use something called symmetric frame field design in order to compute the map. And so how does this work? So starting with a tetrahedral mesh, we then try to solve for a boundary aligned frame field, optimizing over these spherical harmonic coefficients on every tet. And then given the smooth frame field, now we can trace streamlines of the frame field. And that's what's visualized here. And then given the frame field, we can then use it to guide an integration step, which actually explicitly computes this map from the geometric domain to the parametric domain. And then again, given the map, we can go back and obtain a discretization of the original domain. This figure was taken from Liu et al. In 2018. Okay, so that's kind of, we're also partially motivated by this task, and so I wanted to introduce it here for context. But so now let's get into the details. We want to come up with a representation of GL3 mod O where every element of GL3 mod O is represented uniquely. So how can we do this? Well, the key idea is, to understand the key idea, let's first consider this map L2. And L2 takes in three vectors, F1, F2, and F3, and it's going to take an outer product of each of them and sum them together. And here I'm rewriting this formula just a little bit more compactly, but the meaning doesn't change. L2 is just the outer product of each frame vector summed together. And more compactly, even more compactly than that, I'll write these three frame vectors as a capital F. And the first thing that I want to note is that this function is permutation and sign invariant. It's permutation invariant because you're adding together the three outer products, and so addition is abelian, so you're losing the labels 1, 2, 3. And it's sign invariant because outer product, it's like squaring, you lose the sign of F1, F2, and F3. So it's like if you made them negative, it would give you the same matrix. And in particular, for an octahedral frame, L2 is just the identity matrix. But this is a problem because it's the identity matrix for every single octahedral frame. So it doesn't uniquely represent distinct elements of GL3 mod O. And so that's the next thing that we'll discuss. But before I move on, I want to note a way of visualizing this function L2, which is that we can take every point on a sphere and contract it on both sides with this identity matrix, and then rescale that point by the resulting scalar. And so this is a little bit boring for the identity matrix, but in the next slides, you'll see some more complicated figures, which are visualized in essentially the same way, just like contracting a higher order tensor on all sides by a point, and then rescaling the original point by the resulting scalar. Okay, so how do we arrive at an injective representation of symmetric frames? Well, we consider now a family of these maps. And the key difference is that now instead of doing an outer product, we do a kth tensor power. And so now we have this family of maps Lk, and the thing that I want to note is that these maps are still permutation and sign invariant as long as k is even. And so for L2, again, for an octahedral frame, it's a little boring, you just get an identity matrix, but for L4 and L6, you do clearly capture the orientational information in this function. And in our paper, we prove that this is actually sufficient in order to produce an injective representation of rank 3 frames if we take the direct sum of L2, L4, and L6. And this is one of the key contributions of our work. Okay, so now we've introduced the representation that we'll be using. And now in the next section, I want to discuss the symmetric operators which we develop based on this representation and how we combine them together in order to introduce a novel frame field design objective to the geometry processing literature. Okay, so now we want to discuss how to measure smoothness, right? Before we needed to consider 48 different permutations. Now we want to do something different, but the problem is still the same. We have two frames, F and G, that are different from each other, and we want to compare them. Okay, so what we do now is we take the lift of F and we take the lift of G, and again, this is actually three separate tensors that we're keeping track of in a list. And what we do is we do something very similar to what people did for the spherical harmonics. Is we just take the difference of the tensor coefficients with respect to the Frobenius norm, and we sum these up. And uh, there's still more work to be done in studying these smoothness energies, but even this formulation is already quite effective in practice. We find in terms of uh, producing frame fields which are smooth. Okay, so that's our notion of smoothness. Now the question is, well, how do you discretize integrability in this representation? Well, before we discuss how do you discretize symmetric integrability, let's recall how do you discretize vector field integrability on a TET mesh. And so this was studied in Tong et al. 2003. And the key idea is that given a vector field, which is constant per TET, the integrability condition is that the projection of two adjacent vectors, v and u, should agree on every shared facet of the TET mesh. Our notion of symmetric integrability is going to be very similar, except now, again, we have these symmetric tensors on every TET. So our condition is that the projection of these symmetric tensor coefficients to the shared facet must agree for every shared facet. And one thing that I want to point out is that this ends up being similarly a linear condition on the tensor coefficients. Okay, so that's kind of the key contribution of our work. Well, we also introduced several additional fairness measures, which were necessary in order to formulate a design objective, because now we're optimizing over GL3 mod O, but we still kind of prefer frames which are approximately octahedral. So we have a term which penalizes when individual frame vectors are non-orthogonal, when they're non-unit, and we have an extra term on the boundary which pushes boundary frames to stay in the tangent plane. And we combine all of these terms together to obtain a frame field design objective. Okay, and now let's move on to the results. And here are some results we obtained on some more complex animal models. But how do you understand these figures? So in this work, we actually introduced a new visualization technique for understanding how integrable a frame field is. And so how do we visualize things in this paper is that we'll be drawing the resulting parameterization, again, the output of the full parameterization pipeline in gray, and the colorful curves here are samplings of the underlying field streamlines which we obtain, and the goal is to obtain fields which are integrable. So the integration step should not introduce a lot of error. And so how exactly we quantify this, well, there's more details in the paper, but qualitatively what you want to see is that these colorful curves and the gray curves should be very close to each other, and that's what you see in this example. So here is an example of a twisted torus. So this is a triangular prism which is extruded, twisted, and glued together. And here we're just minimizing the E-mesh objective. And in this example, you can see that there's the parameterization is quite poor quality. It somehow doesn't look regular, and there's low agreement between the underlying field streamlines and the parameterization. On the other hand, if you take the same frame field design objective, but also now enforce symmetric integrability like a constraint, now you can see that the resulting parameterization quality is significantly improved. You can see that these gray curves very regularly discretize the underlying geometric domain. Okay, and so here's some additional examples of results from our method on a data set of kind of industrially motivated models called HexMe Industrial. And zooming into one of these models, you can see here are the results from our method, and here are the results from the state-of-the-art frame field solver in the state of the art hex mesh generation pipeline, and that pipeline is kind of producing poor parameterization quality on this example, whereas ours is doing a much better job of the gray curves are kind of mostly look like they're cubes and are discretizing this complex turbofan geometric domain. And also, if you look at the integrability error, so like the global integrability error, so the discrepancy between the parameterization and the streamlines, you can see that our method has much lower integrability residual. And here we have sliced views of the integrability residual. So you can see that it's not only on the surface, but also on the interior that you're seeing this large residual. Okay, and then we also evaluated on a data set of polyhedral models, which we found to be quite useful a quite useful data set to be evaluating on, particularly in the process of development of our method. And here's some empirical results on evaluating the resulting parameterization quality on this data set of polyhedral models. And the key thing to note is that with respect to most of the parameterization quality objectives which we evaluated, our method produced better parameterizations, because it's somehow not entirely straightforward to even answer the question of what makes a parameterization good. And we evaluated with respect to a number of baseline approaches for designing frame fields, and found that our approach where we enforced integrability kind of was useful. And here's an aggregate study. So we found that on both of these data sets, enforcing symmetric integrability consistently reduced both the global and the local integrability residual, which to me is a very promising result, showing that our formulation of symmetric integrability is actually in practice doing the thing that we wanted it to do, which is reduce the amount of integrability residual during the optimization step, which kind of makes the whole frame field design pipeline more sensible. Okay, so that's kind of the key contribution of our work. And so it still doesn't really resolve the question of this volumetric parameterization. How do you globally generate? How do you generally obtain a hex mesh robustly? And one of the problems which still remains is these global topological obstructions. Just because our local integrability residual is small everywhere doesn't guarantee that the resulting frame field admits a global parameterization. And here's a nicely illustrated example of a topological obstruction taken from the paper of Liu and Baums in 2023. Another thing that we don't guarantee is that the singular structure is even locally valid everywhere. And one condition that we know needs to be enforced in order for a symmetric frame field to be meshable rather than integrable is that everywhere the singular structure must have index a quarter, plus minus a quarter, or index 0. On the other hand, it's totally valid for a symmetric frame field to admit an integrable symmetric frame field to admit singularities of index 1/3. So here's an explicit illustration of this. And one thing that I'd like to point out is that these are the sorts of singularities which appear in triaxial weaving. And so here's an illustration of a singularity, of a surface singularity in triaxial weaving. And here I'm superimposing these two sets of singularities to show that actually they're tracing out the same curves. Okay, so thank you for listening to this talk. I hope you found it interesting. The code for our implementation has been published on GitHub and appears at this link, and will also appear in the description of this video. So yeah, thank you for that. And two more things I would like to discuss. One thing that I want to point out is that there's a somewhat subtle point in our formulation, which is that uh, our notion of symmetric integrability and symmetric smoothness, they're both symmetric, but that doesn't guarantee that the notion of symmetry is the same. And this problem was also encountered in Diamanti et al. 2015, where the smoothness matching and the curl matching terms didn't agree. And there they introduced something called a curl quotient in order to enforce this consistency. In our work, we added uh, a significant amount of numerical viscosity to the constraint in order to deal with this problem. And we find that this was a simple and effective remedy, but there's still more research to be done in order to improve this in practice. Another thing I want to point out is that our representation of symmetric frames might sound a little complicated. Why do you need a direct sum of L2, L4, and L6? Well, here's a concrete example which demonstrates that just keeping track of L2 and L4 is not sufficient. So here are two frames which are quite different from each other. They're approximately a 30-degree rotation, one of the other. And for these two frames, actually, in terms of the coefficients, L2 and L4 are identical. So this representation actually can't distinguish between F and G, whereas if you also add L6, these differ from each other, and so that actually is sufficient. And again, in the paper, we prove that the direct sum of L2 and L4 and L6 is an injective representation for GL3 mod O. Thank you for listening to this talk once again, and I hope you found it useful.